Oh, sorry guys, we're just setting up an experiment here.
Oh yeah, Mark. I'm actually we're ahead of schedule. I'm ready for you if you want to present.
Oh yes. Okay, so my apologies. Last week I was presenting, trying to show you guys some videos, and instead of showing you the videos, you guys are all watching my OBS video program setup. So we're just going to go over those videos again, and there is one new one as well. Just bear with me a moment while I pull them up. Okay. Test data. Okay, so hold on a second. Resize that. Share screen. Okay, now can you see this this experimental setup? Tim, can you see it? Is it good?
Yes. Sorry about that. I had you on mute. Yeah. No, it looks great.
Oh, okay. So this was one of the first experiments we ran, and instead of using the large electromagnet, we wanted a gradient magnetic field. So that's a stack of 2 neodymium magnets, and on top of it was the millisaucer with bismuth in it, which is, we call it a millisaucer because it's a millimeter-sized saucer shape, and it has bismuth in the center of it, basically making like a 30-gram sample. The horn antenna dispersed the field a bit, so it was not getting a full 200 watts output, probably getting closer like 1 or 2 watts. And the scale measurement was being read via a mechanical scale over here. And I'm just going to run through it pretty fast. Zooming in on the scale, this is over the course of an hour. We're changing different frequencies. Didn't see any movement in it. The scale remained rock solid. This is when I was going in there just to readjust something. So this setup didn't produce much of a result. The next experiment was using a piece of smelted aluminum that had a little bit of iron in it. So this was the ultra pure aluminum sample that we had. Smelted it, added a little bit of iron, and ended up with a little puck. Same setup. There's a larger magnet this time. Scrolling through it over here, we're not seeing any change on the scale. We're rolling through the frequencies. We're rolling through the magnetic field strength, confirming that the RF was going in. Again, this magnetic field was getting just probably less than 1% of all the RF radiation that was coming out of there, and the skin effect wouldn't have penetrated the sample. So we didn't really see anything happen with this experiment either. Now this is a close-up experiment. This is a millisaucer. Millisaucer is like 30 millimeters across or something like that. It's shaped like a saucer. This one doesn't have anything in it, so it's extremely lightweight. As I recall, the scale was having trouble measuring something so light, and the diamagnetic effects of aluminum started to become very apparent with this setup. And it became hard to get the sample to stick within its comparable magnetic field for EPR to take effect. EPR happens at 28.025 gigahertz per Tesla. So we need a correlation between magnetic field strength and RF frequency in order for that to happen. And it was a very small window when you're using a single magnet like this because of the gradient, of course. So here we're starting it. Again, you see, we did see movement over here, but this is, it just dropped in a second, and then it flew up. So it was basically giving us a hard time, standing in that center area. Again, this sample is very lightweight. We're talking probably like 2 grams total. So then we zeroed it out so that it's very, very lightly touching this surface. But, if it would lift off the surface, we would see that. And with this setup, we didn't see any weight loss. Remove the, let me see, actually, I do see some movement there. Yeah, there is a little movement there. It didn't lose weight, but it did move. It's always fun looking at these movies afterward, because that's when you actually notice what happened. You don't see this while the experiment's actually taking place. So it did move along the surface there. So there was stiction of it sitting on a surface, lightly supported by the string above it. You can see the string even has a kink in it. That's how lightly it was supported, right? And it actually did move along the surface. That's very interesting. Did not notice that before. And then we removed the plastic, the PVC, and it just fell down again, bottomed out. So you can't really get great results in that setup. But this is something that I just noticed right now. Look at it slide across the it's sliding across the base over there. That's pretty interesting. Okay. We'll have to redo that experiment in the near future. This next experiment is, let me get the name of it again. Niobium. So this one was kind of cool. We used, I think it was sample 24 or something like that. Stuck it inside the chamber, turned everything on. Niobium magnesium powder inside of an epoxy. And guess what? It lost weight, but not for any good reason. So we started turning on the RF, and here's what happened. Then this happens pretty quickly. This is a spy camera, by the way. Up on the top left, we're looking through a fiber scope straight into the chamber. And there's a little bit of light in there as well. You're going to see exactly what happens to the sample. And don't forget, it had magnesium powder in there, which is highly flammable. So there, rubber bands popped, scale bottomed out, chamber filled with smoke. Sample basically caught fire, quickly shut off the experiment. It bottomed out because the sample fell out of the sample holder, destroyed the sample holder in the process as well. So at this point, we decided we need to put a thermal temperature sensor device inside these chambers, because we're pumping them with so much energy that we can cause things to go on fire. This next experiment was thick aluminum plate. It was inside a rail system so that it couldn't move from left to right. It could only move up and down, and it couldn't wobble. There was a lot of stiction in this setup. And as you can see, that there was a tiny bit of movement there, but there's a tiny bit of movement in that scale, but not much. That I think was from going inside, and we went inside to check some things, so that wasn't the weight loss. Okay, next experiment was, again, we're doing the business millisaucer, but this time we're doing it with the large electromagnet over here. So this is a homogeneous magnetic field in the bismuth, with the bismuth millisaucer setup. That weighs about an ounce, and it's really, really tiny. I have it right over here. This box somewhere in here. This is that thick aluminum plate that I was talking about a second ago. On here is our temperature sensor that we installed in the chamber. We had to CNC put a special window, a germanium window, to allow for the thermal imaging to come through. That was quite a process. We had to take the entire thing apart and rebuild it. So at this point is when we really get the experiment started. There you can see the RF is in running mode, and that scale is not moving. Moved a little bit, but yeah, it's not really moving. Just a tiny bit. Sample did warm up as well. We didn't see 80% weight loss, as Alzofon said. That's for sure. This is sample number 3. We were a little excited that night. Had a couple friends over on Zoom, and we were doing anti-gravity experiments with aluminum powder inside of epoxy. Now in this setup, you can see the temperature reading over there. Those are in degrees centigrade. So we were monitoring temperature as we're going through these experiments. We had to shut down the experiment every once in a while because the temperature, as soon as it got near boiling, I started, getting concerned that we would again melt the plastic sample holder or the string that was holding it. So we had to take breaks through this experiment process. It was about an hour long. There was a little weight loss there. I guess we're get a little bit more, and we set up a that was the radio that we set up for listening to the static. But we're concentrating on that scale on the bottom left. There is a couple bumps over there in the beginning, but so there might have been a little bit of weight loss, but in terms of actual usability in a craft, the sample, at least this setup, it was warming up so quickly, really became very useless as a propulsion system, at least in that iteration. The force meter, it should be ignored. That is not part of the experiment. The potential shows, I think, there's a shunt on the electromagnet, and that's the voltage across the shunt. So for monitoring the magnetic field strength, but we've since shifted to a new system where we put a Gauss meter directly on the electromagnet. So we read that to get our electromagnet readings. Actually, Tom, we got to set that up. Can you grab a piece of copper tape? Got to set that up for our live experiment. Okay, so this is an experiment that we actually saw something very interesting happen. This is osmium, a little piece of pellet of osmium that was wrapped in an aluminum foil mylar blanket, which is extremely thin aluminum. Now, the sample in this did lose weight over time of significance. See that? There was also a movement in that string as well that did coincide with it, so that may have caused an error in the reading. But I did notice in this experiment, I think it was around 23 minutes in or something like that, there was a movement in the sample right when the frequency of the magnetic field matched up, right when resonance should have been happening. And the sample twisted a little bit, and that we saw that on the spy cam, which is on the top left of the screen. That was pretty interesting. We're going to try replicating this experiment today, and we're going to do it using a instead of a chamber, we're going to have it in open air with a waveguide pumping the RF into the entire Faraday cage behind me. So it's another variation of that experiment. And that is one of the last experiments we did. There's one more experiment, but it's in a different folder. Let me pull it out. So we also ran one on just the other day. Okay, there we go. Yeah. So this is a sample of ruby. Now, why are we using ruby? Ruby is aluminum, silicon, and oxygen as well. And so it's basically aluminum, which is a one of the stronger participants in dynamic nuclear orientation. It's a compound of it. This is also what George Hathaway used in his experiment. Now, in this setup, we did away with the scale, with the mechanical scale, because we managed to get a very sensitive digital scale that is outside of the Faraday cage. So it's literally on top of the Faraday cage. There's a hole through the Faraday cage, string drop down from the bottom of the scale. I first ran a null test with nothing on the scale just to make sure that it wasn't getting interference from RF. No interference. So we're finally able to use this mechanical scale over here, this digital scale, I mean. Here we're getting live feeds from the scale on the right. It does have a bit of a drift depending on temperature. So when the heat turns on in the room, you could see turns on or off. You can see a slight drift over there. Yeah, I think that's what we were looking at with these numbers. Although I did notice that there was spikes in weight loss. Not in this setup. Actually, it would be the next experiment that happened. So the numbers are pretty. They're just changing with the temperature in the room. I guess that changes some of the electronics on board. And that's just the nature of these scales. Okay, so in this setup, we covered it with that same aluminum mylar sheet, which is like an emergency blanket that the Red Cross will give out. So upon powering it up initially, you can see it sort of gets crushed over there. That's from the RF was too powerful. We had to tone down the RF quite a bit. You see, I see negative 26 decibels. I think I dropped it to like negative 50 or negative 40 decibels. So in this setup, there was much more drastic changes. You see here changes of like 5 micrograms, or those would be 50 micrograms at a time. And it was going up and down in all directions. We did notice a correlation between the pulse lengths that we put in and sudden weight losses. It was going in all directions with the weight loss. Again, the sample is not in a perfectly homogeneous field because we couldn't get it to line up horizontally. We'd always want to go in the path of the magnetic field. But you can see here that there were much more drastic changes than what temperature itself can create with our scale system. Of course, a future step would be to isolate the scale thermally in a small chamber, but you know, that's for a later date. Then we'll have rock solid numbers. When I pumped up the power pretty powerfully toward the end, we saw the most dramatic weight losses, and that's when I took the sample off. We did see much more dramatic weight losses when I pumped the power up to full, and this was with ruby and covered in aluminum. Okay, any questions yet?
Yeah, I have one.
Yeah.
Sure, go ahead, Riccardo.
Yeah. So look, first of all, Mark, absolutely excellent the work that you're doing, and I've got to say, I feel like someone that's coming in cold to this conference series. I feel like I'm watching history being made. So yeah, really well done on what you have been doing and what you've just done now. So that's the first thing I just wanted to say. Second, my actual question is, looking at what you're doing, and I know what Todd's doing, and I've sort of already floated this question to everybody there, but I'm going to put it to you now. Would a discussion around the history of the cosmos, and there have been instances that I believe I can demonstrate where the environment for faster than light travel has occurred naturally, right? Would a discussion in that space assist you in any way, do you think, in helping you to design experiments or things that you might need to consider? Would you welcome some kind of discussion on that point?
Of the origin of the cosmos?
Well, no. So let's, I'll just simplify it. So you've got the Big Bang, you've got now. Between the Big Bang and now, right? And an example is cosmological inflation, where the cosmos inflated in the first, 10 to the minus 23 seconds, and you had an environment where space-time was literally traveling much faster than light. And if you map the history of the cosmos in terms of cosmological constant and stuff like this, you can see in the history of the cosmos that there have been instances where the speed of light has been c. It's not actually c now. It was more c. It was faster than c in the past. Would a discussion covering that and looking at the conditions, like what the temperature was, etc., all these kinds of stuff, would a discussion in that space assist you in any way, do you think, in helping you designing experiments that you're doing now? Is it going to assist you? Is it going to give you any ideas, any clues?
I don't know.
What do you think?
I'm not really sure how the two are related.
Well, I mean, I know in Todd's case, for example, he's looking at modifying the space-time manifold through an analysis of, harmonic oscillators, and much of what he's doing now is aimed towards demonstrating how space-time can be the manifold can actually be manipulated. So I'm wondering whether the work that you're doing might get some kind of insightful advantage, give you some ideas, some that you might not necessarily have thought to go in the past.
I mean, you're asking me if it's going to tell me something that I didn't know, which I can't know. That's an unknowable that I can't know until we've had those conversations and we know.
Yeah, fair enough. Okay, all right. Look, I was just like I said, I was impressed by what you've done.
Thank you.
I was just wondering, whether a discussion in that area might give you some more ideas around different experiments and et cetera, et cetera.
I mean, we have ideas for lots of experiments. We have lots of experiments that are half finished too. The issue is that ideas are a lot cheaper than action by many orders of magnitude. There's probably, for every 1,000 ideas, there's one person who actually does anything. And that person who does something has ideas of his own. So there's a lot more ideas running
fair
around.
enough, okay.
There's a lot more ideas running around than there are people who are doing anything with it. And we're trying to fill that gap with more people that are doing stuff about it.
Yeah,
so these experiments surround EPR, electron paramagnetic resonance, which is the Alzofon experiment. Basically, we're trying to orient the subatomic particle spins in the core of an atom using the valence electron's spin, energizing the spin using EPR. Basically, get magnetic field, which makes the electrons process in a more coherent way. Depending on the strength of the magnetic field, they process faster. So there's correlation between magnetic field strength and frequency of the electron's precession. And we know what that ratio is. It's 28.025 gigahertz per Tesla. And by hitting the electrons at that frequency with that correct magnetic field, you're able to pulse it and that then transfers its orientation as extra energy to the core of the atom, and the core then becomes more coherent. And we believe that when you have this coherent matter state, it will no longer connect to incoherent matter, such as the Earth and the cosmos. And it will be free from the restraints of inertia and gravity, but only along its plane of axes and its plane of spin and its axes, which explains why flying saucers cannot do a barrel roll, because they're just flying along a flat plane. They can do 90-degree turn at 10,000 miles an hour, but they can't go like that. So this experiment we have set up right over here that you see surrounding me is the osmium with the what you call it, with the aluminum on it. And we're going to power this up in a moment and see what it does. But first, I need to get the Gauss meter installed. So just give us about 2 minutes. We'll get that done, and I'll be right back. Okay.
Good.
Okay. So we're waiting for Mark here.